waxing on a picture and I think it's wax marble.
Well, good afternoon, everybody.
Good afternoon, Myers.
How's it going? I'm glad all of you could make it today. We're going to explore static electricity, and I'm expecting a few more people to trickle in as we go. We'll add them in as we get things started here. So yes, welcome once again. I'm Chris Meyer, in case we haven't met before. And today, and the resources that I'm showing you are available on my website here. So if you jot down that URL, you'll be able to download copies of what we're using today. And you'll also be able to take a look at the videos, just like the one that I was showing you there, of this static electricity lesson in action with my grade 12 students. Amongst other things. So, variety of things for you. But first thing as we're getting started, we have to have a word from our sponsor. So today's snacks are brought to you courtesy of the Ontario Association of Physics Teachers. A really awesome bunch of teachers to hang out with. A mental note. So you'll find us with a booth at the upcoming STAO conference. As well, we have our own conference in May. And so we're trying to help people with their physics stuff and helping you to learn how to teach well. So two important goals that we have with our organization. So please check us out. Check out our conference. Really good bunch of people to hang out with.
Great newsletter.
And have you seen the newsletter? It's styling and profiling. So, what I want to do today, I have two goals for you, but all of them are to help you become a master teacher at whatever it is that you might be doing. Now, to become a master teacher, there's really two important facets to your professional practice. One is mastery of content knowledge. So in part, today is to help you deal with that. So learn about the details of the concepts as well as the scientific process that goes into developing that understanding. And the other half of being a master teacher is developing your pedagogical knowledge. So this is your understanding of how students learn and the different techniques that we as educators can use to make that most effective and efficient. And just like the chocolate and the peanut butter, when you put them together, you get something quite magical. So you get the pedagogical content knowledge. So the experience and the understanding to know that this is the kind of pedagogical strategy to help with this student difficulty or misconception for this particular topic. And as master teachers, we want to build up our repertoire of pedagogical and content knowledge so we feel confident that we can deploy effective strategies that will help our students learn. And so in today's workshop, we're going to attack this from two different sides, depending on where you are approaching this topic of static electricity, because we're all coming from different directions here. Could I see a show of hands? How many people are interested in this topic because of you're teaching grade 9 science? Just a quick show of hands. So we have the grade 9 science people. And how many people for, I think it appears in grade 6. Did we get any of our grade 6 teachers? No, they didn't make it today. And then for the grade 12 physics, for its treatment in there. Okay, so we have a few more for that. So depending on where you are with your own comfort level with these two sides of the coin, when we go through our workshop today, you should think about a different focus. So today you're going to work through the exact same investigation that I give to my grade 12 students when we begin our unit on electric fields. I learned quickly in the past that they have no ability to reason about how electric charges work in solid matter unless we carefully review the grade 9 material and help them to deepen their understanding of it. So even though it's not really a part of grade 12, it's now an important part of my unit because it's so critical for building their good understanding of what they're doing later. So this is the investigation that we're about to start out. And I want you to think carefully about your strategy for today. So your personal goal for this workshop might be to focus on your content knowledge. So you personally want to understand better what's happening to the charged particles within solid matter when we do these kinds of experiments. And in that case, go through the investigation and answer the questions just like you would want your own students to do. So you're building your understanding as you go through. Or your goal may be on the pedagogical side, so you might feel confident with the content knowledge. But in that case, I want you to think very carefully about how the lesson is structured, the sequence of ideas, how the ideas are built up, and for each question, each step within the lesson, think about what student difficulties might arise. So what conceptual challenges they might face, and how you as a teacher, or how the structure of this particular lesson helps them to think about those difficulties and resolve them. And finally, static electricity. If you've tried these experiments with your students, you've had the experience of, yay, today we're going to do static electricity experiments, and then nothing works. When I tried these experiments yesterday, nothing worked. And I tried them today, and it's better. It's definitely better. I'm keeping the windows open to try to get some of the cold, dry air into the room. But you really can't fight nature on this. So you either have to wait for a good day to do the experiments, or you have to have your plan B worked out. And so I have videos of all the experiments in action. So if it doesn't work out, I say, okay, stop the class, you take a look at this video. This is what's supposed to happen. But it's also worthwhile taking some time thinking about why the experiment is failing, because it will happen to you if you are leading this. And as you learn more about how static electricity works, you learn that it is wonderfully complicated. And those water molecules that are floating in the air cause all sorts of trouble for us. Now, for example, I have my equipment that we usually use at the back for the experiments you're going to try out. And I was trying it, and it was just working so-so. I picked up some fresh pieces of acetate for today, just straight out of the package here. Tried it, much better. So my theory is there is a lot of water molecules that have attached themselves to the surface of the acetate in those drawers, and that's interfering with the static processes. So this is part of understanding the equipment better and the content better in order to help you with the flow of your lessons, because you will deal with these problems with your own students. So it's good to think about why it's not working well. But we don't want to spend too much time on that, because I want to make sure that you're targeting your main goals here. But please feel free to ask me as you go along if the demonstration or the experiment's not working out properly, and I can come over and help you out as I would instruct my students, and I can also give you the more detailed perspective on what's going on. And I'm glad you mentioned that, because if during your work today you'd like to draw some quick sketches of things, in your tables there's a white basket with our markers, and there's whiteboards along the side, so you can quickly grab, sketch, discuss with your neighbors. So, what I want to do is have you work on this in groups of 2 or 3. Have your personal goal in mind of these goals here, and work through the questions, talk about them, and so just go where the discussion of your group leads. I have the equipment you'll need at the back of the classroom. Ladies and gentlemen, let's pause for a moment here. This is what I routinely do with my class to get going, so you're doing your thing, and then I'll stop the class for just a brief discussion. Now, you folks are already demonstrating much more expertise than a typical student, and I can see you doing some fairly sophisticated things. So I just want to point out some of the difficulties that students have, because you've been successful getting them to attract when you have the acetate and the ebonite rod, and I see a lot of people doing this. Why? Because often, you know, the students will just try to do this, but people are doing this. What's special? Why? Why are they doing it? Why are you doing this?
Increased surface area.
It's the area that you run as well.
Yes.
Right? Our students don't understand that. And this is one of the challenges of getting these experiments to work. the static electric charge on insulating materials, and this is an example of that, are localized. So they stay wherever the rubbing occurred on the object. This is why I no longer use balloons, because they'll rub one side of a balloon, it'll rotate, and then you have the uncharged side, and you get a totally different response from what you're hoping for. But for this one, it does help if you bend the rubbed area close by, and that's one of the little tricks of the trade. It's learning and making sure your students understand, well, it's the rubbed spot where something happened. We don't know what the something is yet, but it seems to stay in that area. And especially at a younger grade with grade 9s, that's worth spending much more time exploring than I do with my grade 12s. The fact that it's just the rubbed spot of the balloon that seems to have some mysterious effect. Please keep going. Ladies and gentlemen, a question came up. Doing that first set of experiments, sometimes if you charge both ebonite rods, you put one on the watch glass, you bring them together, they attract instead of repel. This happens a fair bit, and we need to, at least to ourselves, be able to explain what's happening. Why do you think that happens? Chicken?
Maybe you accidentally grounded it
Uh-huh.
with your hand.
And so what's the situation in that case? Is it two charged objects?
No, one is neutral and one is
Neutral.
charged.
One is neutral.
Now, I've found that can commonly happen.
Charged by
Sorry?
induction. The second one, which was neutralized because we passed it, it's now charged by induction.
So if you did accidentally touch it, then its net charge would be 0. So that could be the reason. But I've seen it happen many times when the students have done it very carefully. Why? And it's a real pain.
Is the molecule on the air?
So the air is slowly, even right now on a fairly dry day, the air is slowly discharging these objects as water molecules bump into them. On a really humid day, they can completely discharge in less than a second's time. You can, if you have a decent electroscope, on a really humid day, you can give it a charge and you can watch that needle drop down under a second. So the air and its water molecules are a real impediment for the success of our experiments. So often the objects discharge their charge before the students have an opportunity to work with them. And then they're studying a different situation from what we're hoping. So you need to keep that in mind when you're coaching them on what's happening and trying to figure out, oh my gosh, it's not working. What do we do now?
Just one comment about, in one of the schools that I taught, depending on which semester 1 or semester 2 this is being taught, they chose electricity to be introduced at the beginning of the semester or towards the end. Like if semester 1, you can just start with chemistry, I'm talking about grade 9. In winter time, you can just have electricity, and in semester 2, you can start with electricity.
Yeah, if you can time it, that's certainly the best thing to do.
In semester schools, it's ideal.
I'm not sure how the topic of the law of electric charges is treated in most introductory texts, but often it is confused with another set of related ideas. Because there's two ways of thinking about it. You can think about the law of electric charges for elementary particles, and that is clear and straightforward, because if you have your two electrons being together, they will repel. Electron and proton, they will attract, and that's about all there is to the story. But when you have macroscopic objects, large pieces of solid matter, the story is different, because then you have neutral objects. And our law of electric charges for elementary particles doesn't easily apply to that. And so I think it's helpful, especially at the grade 9 level, distinguishing, are we talking about elementary particles, the most basic rules for how this works, or are we talking about large chunks of matter? Because in that case, neutral can attract charged. And that seems, or it can conflict in students' minds if they don't recognize that this is really a different set of rules. One applies to these littlest guys, and one applies to large chunks of matter. Yeah, Roberta?
But do you want another, like a different set of rules? It's the same set of rules, but as long as you
bring in the idea of how far apart the charges are. Like, do you not want to use the same rule, or are you going to do that later?
I would say it depends on where you are in the learning process. Because initially, if you're doing experiments and you are putting together, you're building their understanding from observations, then they will be noticing that neutral objects are attracted to charged objects. And as we go through today's investigation, you'll notice where we start to explore in detail what's happening with the neutral objects. Now, one thing that I do want you to do as you get back to your work, because I'm talking way too much for my normal classroom here, is when you get to question number 3, I would like your group on a small whiteboard to draw the corrected diagram for the charge distribution in that hunk of matter. Okay? Please keep going. So you have some great discussions. Now I want to mention a bit about the pedagogy of what you're going through here with the charge diagrams and 2 aspects of it. One is why I've chosen to draw the diagrams this way, and the other is why I've chosen to ask that specific question of, okay, here's a typical student diagram. What I've discovered from my teaching is it's possible for the bright students to answer questions so quickly that they haven't even considered some tempting wrong answers and don't realize that they still carry part of that misunderstanding with them. They don't realize that it's there, but it often still is, and it comes out in other situations. So a very common question that I have them answer is, here is this student's response. So I'm forcing them to deal with this particular common difficulty or misconception. Speaking of which, this is a diagram of a neutral object that's brought near a negatively charged object from one of the best physics textbooks around. This is by a leader in the physics education research world, Edward Reddish. And I think it's terrible. And it shows the wrong ideas. And I want to present this as a counterpoint to what we are doing.
Yes. Yes.
So this is their diagram of what's happening in this metal object, which is brought near the charged object. And I think there's a serious problem with this that leads to genuine misunderstanding with our students. So here's the original hunk of matter. And then one side of it is rubbed and acquires negative charge. And this is what the student draws. And now I've asked you to draw an improved diagram. With my own students, the next step I do in different ways, depending on my mood and the needs of the students. Sometimes I just ask them to place their diagrams along the side. Take a look at each one and decide what you need to improve about your own diagram. Often that's enough to help them understand what the difficulties are. Sometimes I'll have groups hold them up and present, why did you choose to draw it this way? But I think it's very helpful to show this overlapping of charges where you have a positive ionic core representing everything except that one electron that is free to move, or that could possibly move, and then the negative representing that. And in our corrected version, what we want to show, what we want to make really clear, is that when you charge this object, the only moving parts are the electrons, and it's an addition of electrons to the object. This idea is really challenging for my grade 12 students. It takes a lot of discussion, effort, and we revisit this idea so often, and I use this exact model in my class. Here is a representation of our physical understanding of solid matter. What does the red object represent? This is what I say to them. What does the red object represent? It could represent an atom or even a molecule. And then what do the springs represent? The bonds that are connecting them together into a fairly rigid piece of matter. And so if I pull a valence electron, and I like to use that word with my grade 12s because it connects to chemistry. If I pull a valence electron off of this one, that electron is now somewhere else. But what's left? That positive ionic core, which is firmly held in place. And I discuss this over and over again. I go from group to group, talking about them carefully, and it takes a lot of time before this idea is firmly ingrained. So one of the important things to understand in developing your pedagogical content knowledge is understanding that some ideas take a long time for students to assimilate at a deep level. And you have to revisit them again and again and again. It's not enough to say it that once at the start of the lesson, even if you put a box around it on your note in the board. It's not nearly enough. You have to give them situations where they are required to use that idea in new circumstances to test how well they are assimilating that concept. And this one is, I've found, surprisingly challenging for them. The positive hunks, the ionic cores, do not move in solid matter. Ladies and gentlemen, please keep going. When your group is ready, you're welcome to try out the next pieces of equipment. Hey, ladies and gentlemen, one last thing that I'd like to show you. To help complete our picture of the charges and the types of diagrams that my students make use of. Here I have our neutral object. Here I have our negatively charged object. So this might be the ebonite rod. Bring it by another ebonite rod. And as you bring these closer, the charges shift. And so I'm teaching them to use this notation for insulating materials, showing that this electron of this neutral atom or molecule is just now pushed to one side. And so the positives kind of see the negatives over here, and we're now getting an attractive effect. I find this diagrammatic tool is very helpful for helping their understanding.
Yeah, it's a nice distinction to the insulators versus conductors.
Yeah, and then you can talk about the difference between what's happening in an insulator and a conductor.
How come it's not negative repel, and then you emphasize negative and positive?
I'm sorry?
You emphasize the negative and the positive attract.
Right.
How about the negative and that negative repel?
Well, that's a really good question. And, ladies and gentlemen, this is a really good point because we know that these guys are attracting, but this one's still here. And we know that negative repels. But we see attraction taking place. So what is that telling us about the strength of this interaction compared with the strength of that interaction?
The positive charge is strong.
But they're the same size charges, but this is weaker than that. So this is our first glimpse that there's another idea to this electrostatic interaction, that distance plays a role. And in the following lesson, my students will begin to develop their understanding of Coulomb's law. So this we can't fully explain yet, but based on our observations, we can start to see that distance is a factor here. And it's getting them warmed up to that.
Two difference in distance matters.
Yes.
There's a really little difference between the positive, negative, and negative, and negative.
It's very, very small, but generally there's a large quantity of charges involved. And it's enough because the electric force is such a powerful force compared to others, weakling gravity, that's enough to make these, well, gentle effects noticeable between the charged and the neutral object.
Being a naive student at this point, I could also offer an explanation that somehow the positive attraction shields from that negative, because No, but I'm pretending I'm a student, and that's my theory. And then the next day, we see there's this distance relationship, and I don't have to have some magical shield of whichever one's closer.
Right. So, ladies and gentlemen, those are the main points behind the pedagogical process that I use for teaching this topic, and some of the diagrammatic techniques. So, you're welcome to hang around for a little bit, try out a little more, or some of the experiments if you like. But otherwise, I think we can wrap up for today. But thank you all for coming. I hope you found it helpful and useful. And I'll put my website back up so you can get that URL if you want to download this worksheet or look at any other of the materials that I have for my physics courses. So thank you very much, everybody.
Thank you, Chris. Also, may I recommend that you take a look. He's taped himself. Just terribly brave. He's taped himself teaching a real class with real students, real interactions. So you can see as the lesson goes through, and he's got the little comments underneath. I've been finding these incredibly helpful to see how it plays out in a class. How do you manage the groups and so forth? So what's the easiest way to get to those videos?
Go to my website.
Website.
If you go to my website here, you'll find the link for all of my electronic resources and my classroom videos. Okay. So if you don't mind helping tidy things up, make sure the table area is nice and clean, materials put back,